we had that first flight. There were 4 remaining to round out our 5 total in our 30 days. And thankfully, at the end of those 30 days, Ingenuity was still healthy. The Perseverance team and NASA decided there's value here in continuing to fly on Mars. Ingenuity can act as a scout. We can fly to a cliff wall. We can dive down into a cave, right? We can go to very high altitude and loiter or do a lawnmower pattern over a region of interest, for example. Ingenuity today is already providing reconnaissance for the Perseverance rover.
Sent ahead as a scout, Ingenuity sent high-resolution images to help Perseverance find its way to the Delta. On its 26th reconnaissance flight, Ingenuity even found the burst heat shield and parachute from the rover's landing. The route was clear. Now Perseverance could tackle its real mission, the search for traces of life on Mars.
We weren't looking for some macroscopic animal roaming around. That would have been easy. No, we were looking for traces of life that already existed on Earth at that time, and maybe on Mars. Primitive bacteria.
Michel Vizo is a veterinarian and works as a scientific consultant for the French space agency CNES. He is one of the world's leading experts in exobiology.
When we talk about extraterrestrial life, we focus on the simplest microbiological form, microbes. So if we find bacterial traces on Mars, we've found a new form of life. If we find a concrete trace of life, even fossilized, that is evidence of another life form in the universe. That's what we're looking for, even if it doesn't lead to Martians.
There was a period of 500 million or perhaps even 1 billion years when conditions on Mars were suitable for life. But was that enough for life to actually develop? I tend to think so, because chemical traces prove that 3.7 billion years ago, life emerged in Earth's oceans. I would like to believe that the same thing happened on Mars. And if life developed on Mars, where is it now?
Où est-elle aujourd'hui?
After a 5-kilometer journey, Perseverance finally reached the Jezero crater delta.
If the origins of life evolved from some prebiotic chemistry, then it most likely would have been in an environment of carbonates and clay minerals. So these are primarily what we're looking for.
We think that certain organisms living in very particular places on Earth today could also develop in certain microenvironments on Mars.
Purificación López García specializes in microorganisms that thrive in extreme environments. The hydrothermal Dalal area in northern Ethiopia is certainly one of the most impressive examples of a biosystem where life seems impossible. But despite extreme temperatures and acidity levels, single-celled organisms can be found in some areas.
At
the edges of Dallol, there are ecosystems sustaining life, particularly archaea. These are unicellular microorganisms, like bacteria, particularly well adapted to very high temperatures of up to 120 degrees and extremely fluctuating pH levels. Studying these extramorphiles lets us better define conditions in which life could have appeared and persisted in extraterrestrial systems. If life emerged on Mars that could survive under such conditions, it could effectively exist in these systems as well, provided there was liquid water and an energy source.
Unlike the Earth, the Martian crust has never been reshaped by plate tectonics. This allows Perseverance to examine very old clay minerals. If there was once life on Mars, these minerals might still contain its components, like nitrogen or carbon.
To find intact organic molecules, it's best to dig a little deeper. And the rover's core can drill holes several centimeters beneath the surface to penetrate rock where they've been protected for millions or even billions of years.
Perseverance took its first sample of soil that might contain traces of organic material.
I would argue that that sample catching system is just as complex as the rest of the rover. It has to be able to take sample cores from the surface of Mars, process them, put them in the tube, and then pass that tube to another robotic arm inside the rover that then takes pictures, does some certain analyses of those samples, seals them because the samples are going to stay on Mars for a long time, and then it has the ability to deposit those sample caches on the surface of Mars.
We hope these samples will one day come back for lab analysis. To conduct a detailed sediment analysis, we need a laboratory with electron microscopes and high-resolution chemistry. That's not possible on a rover.
Perseverance will only store some of the tubes, not all of them. So rather than make one big pile with all the tubes and risk losing them all if the mission aborts, we leave a trail of scattered piles, like Hansel and Gretel leaving a trail of breadcrumbs.
They hope to eventually recover the samples from Mars and bring them to Earth for analysis. It's an ambitious project, especially because it's not yet clear exactly how this would work.
If you thought that collecting those samples and dropping them on the surface of Mars was already extraordinary and hard enough, eventually we're going to want to go bring those back. And so the teams here at the Jet Propulsion Lab and at NASA are already working on thinking as to how we might want to do that.
That's the first time we're going to launch something off of another planet. And then we have to bring it back home here to Earth and bring those samples back home safely and keep them contained. There are any number of challenges here that kind of dwarf anything we've done before.
The space flight system for the return mission should be ready in a few years. Researchers are already working on the new assignment.
These tubes will be recovered by a European-built rover, which will gather them with an arm, put them in a basket, and deliver them to a rocket, which shoots the container and its tubes into orbit around Mars.